So, polymers then. This video is going to run through polymers. It's going to cover the whole of the section of polymers from the A2 specification. So this is Unit 4. Polymers then. So what are polymers? Now, polymers came up a little bit in the AS. I think it was Unit 2, but not to a great extent. But most people, I would guess, do the GCSE, where polymers do come up, I think, in all specifications. So polymers, what are they? Well, long chain molecules, and they really are quite long, sort of, thousands of thousands of atoms long. Long chain molecules made from many monomers. So monomers are the things that go together, that join together to make polymers. So lots of monomers come together to make a polymer chain of this long chain molecule. There are two flavours of polymers in the A2 specification. They are addition polymers and they are condensation polymers. Addition tends to be the one that people do lower down, sort of year 10, year 11, somewhere like that, of the English system. So addition polymers there. Condensation, we're new to most people, but nothing particularly difficult about condensation polymers at all. I'm going to start with addition, then go on to condensation, and then end with a bit of disposable polymers, which is really going to be a table just for you guys to look at and to copy down. So the first one, addition polymers. So the term addition. So addition. What does addition mean? Well, addition means that addition reactions are when you add two or more molecules produce one molecule. There are no other products formed at all. So there's no water formed, there's no methane, no hydrogen chloride, there's nothing else formed even. So two things go together to form one molecule. Or two or more, I should say. So in the case of addition polymerization, we're dealing with alkenes. So for example, we're dealing with ethene. So let's draw some ethene. So here's my ethene. Now I'm saying that n numbers of ethene, could be any number. It could be 1,000,000, could be 3. In reality, it's probably several thousand, tens of thousands. That goes to form me a strand of polyethene. Or if you think about plastic bags and things, then polythene is the same thing, or polyethylene it's also called, and that looks something like this. Now, this means that this part here, this portion, is going to be repeated n number of times. So it's completely dependent upon how many initial ethenes go into this. So 1,000 ethenes would make 1,000 lots of this portion here. Now the buzzword, or the buzz phrase in the A2 chemistry with relation to polymers is this term repeating unit. So I'll just rub these out. It gives me a little bit extra room. So this term repeating unit. This is not a repeating unit, and I can't stress that enough. That is not a repeating unit. If you are asked for a repeating unit and you draw that, you are not going to get the mark. That is not a repeating unit. They often will let it go once, but if there's another question and you do it like this, they will penalise you. Okay, so often they will let it go once. The repeating unit is actually a little more simple than this, but it's very, very similar. So in the case of the polyethene, the repeating unit is going to be that, and that is it. This is the repeating unit, and that's going to be the same no matter what type of polymerization we're looking at. No brackets, no ends. It's just the sort of bare bones of the molecule, the part that's being repeated. Note the trailing bonds, though. That is incredibly important. If you were to do this just like that, you're going to lose yourself a mark, because that can't actually repeat, can it? You need those trailing bonds because it shows you've got an understanding, and therefore the repetition can occur. So that would be the repeating unit of polyethene. Another example of an addition polymer you might get something a little bit more difficult. So you might get something like, they might give you a monomer, give you the alkene, and expect you to draw the repeating unit. So from a past paper there was this. So it was molecule like this. So what's this? 1, 2, 3, 4, 5. Pentuene. So pentuene, and they were asking for the repeating unit. So if we were to look at what this would form, well, it would form a polymer like this. Just bring these bonds at right angles, and it makes the whole thing very, very easy. So CH3, CH2, CH3 there. So that's what it would form. That's what that's the reaction for the formation of the polymer. This is the polymer here. Obviously, you can't draw it out in its entirety. The repeating unit, on the other hand, would just be this thing again without the brackets. So carbon, hydrogen, CH3, CH2, CH3, trailing bonds. That is the repeating unit. And again, as I said earlier on, note that there are no extra products formed here. We just have the however many of this going in to make one huge long molecule, and that's addition polymerization. Quite straightforward, a simple type of polymerization to sort of to lead you into it. The next type then is of course condensation polymerization, and condensation polymerization again. It seems to say this a lot, but it isn't overly difficult at all. You've just got to remember a little bit more than with the addition polymerization. So condensation, I say condensation polymers. So condensation polymers is when two or more molecules react to form one molecule plus water. Now the number of water is obviously dependent upon how many initial molecules you've got, but water is produced here, and that's where this term condensation comes in. It's a nice sort of reminder really. Condensation, water is going to be produced. What we tend to find, and I'll give you some examples and you'll see what I mean here. So we'll take an example of something like this. So we've got a molecule here, OH group on one end. We've got, yeah, we'll go with that. That's our molecule, and this could be a molecule Y, as it was in an exam paper question actually. So this is Y right here, and what the question was basically draw the repeating unit that would occur when a polymer is made from Y, something like that. So again, you could go through and you could do your calculation and all the rest, but this is actually quite straightforward the way this is working. And if you can remember this, it will speed this up greatly. Basically, the way all of these condensation polymers work is we have a reaction between an OH group and an H, and that's where this water comes from. So that's how the polymers actually link, and you can see on the ends of here, in this case we have two OH groups. So what we're going to end up forming is, and I'll draw this out as the repeating unit and then explain sort of what's happening afterwards. So there's your CH, there's your C double bond to O, and then we're going across. So this is the repeating unit for this molecule here. Now there are a couple of options here of what you could do. This bit in the middle must stay the same. I could put the O there, but then I would have to remove it from this side. If I want to put the O this side, I can't have it on this side. The reason being that oxygen, we're assuming that either the OH is going to be removed from this side, reacting with the H of the next molecule, or the OH of this side is going to react with the H of the next molecule, and that's got to stay constant. So if I have O's on each side, that is actually now incorrect. That's not right, because actually, if you think about it, that couldn't possibly form me water when it reacts with the next thing. So actually, you've got to have the O on one side or the next. It doesn't matter which side, but it must appear on one of them. Again, with these trailing bonds. And in this case here, when one of these reacts, we would obviously produce water again. and that's this part here. So the OH group is reacting with the H of the next molecule, or the OH on this side is reacting with the H of the next molecule. It doesn't matter. In fact, I want to show you here. I'll just draw this out so you can actually see what I mean. Just draw one more molecule for you. So that would be the next molecule, and basically what I'm suggesting here is that in the case of what I've drawn here, the repeating unit would be this reacting there, so my OH coming off as H2O. If I wanted to switch this and put the O on the other side, then I would be suggesting there that in fact that would be happening. So very slight difference, very slight difference, but at the same time it's important to make sure that O is present on one end, particularly in these cases. And what I've formed here, this is a polyester. So it's an ester linkage. This part here is ester linkage that's going to connect up our each one of our monomers to form the overall polymer. So it's polyester, ester linkage, and that's obviously they do tend to, well, they certainly do ask you that occasionally, kind of what kind of polymer would this be, etc., etc. And that's obviously important that you can specify that this type here is a polyester. The easiest way to remember that is that we have an alcohol group, an OH group here, reacting with a carboxyl group. And that's really, if you remember back to sort of formation of esters, we have alcohols and carboxylic acids coming together to form an ester. So what you're forming is a polyester. Lots of esters joined together, really. So that's your first type, and that's just a generic one. There's nothing there. That was just an application, really, of a molecule that was given to you and you were expected then to draw the next thing from it. Then this one, however, the formation of pterylene, or PET, as it's also known. This is a reaction you're expected to be able to remember. So you need to know this one. You need to know the reactants, and you need to know, obviously, that it produces pterylene. Now, the reactants in this example are as follows. We have benzene 1,4 dicarboxylic acid, and we're going to react that with an alcohol. So again, this is a polyester. React that with an alcohol, so OH group here. We're going to react that with ethane, one, two, diol. All I would say here is make sure you get that E there. They love that in an exam to penalise you for ethan 1,2-diol. Must have an E there. And they could actually give you a bigger one. This, not in the case of pterylene, that's formed from this. They could give you a longer alcohol and expect you to name it, in which case it would stand true. If there were 4 carbons here, it would be butane. With the OHs on the end, it would be butane 1,4-diol. But of course, this one here, just the 2 carbons, it's ethane 1,2-diol. Numbering is obviously very important there as well. Don't think that, oh, we shouldn't include the numbers, because obviously it's dictating that the OH groups are on either end of the molecule. Now, when these come together, same kind of reaction as before happens. So I'm going to draw the repeating unit, and the repeating unit, I'm going to do it this way. But again, you could switch it over, and I'll explain what I mean by that in a second if you don't understand. So there's our benzene ring there, C double bond to the O. We have an O ester linkage linking us to the carbon, carbon with the hydrogen, 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 and then on this side, I'm going to have my O. Now, I'm choosing for this time to say that the O is because of this hydrogen being joined to the OH there. I could flip it round and say I'll have O there and I'll only have the blank there. It doesn't matter. I just quite like to draw it with the O this way. Again, with the trailing bonds. Doesn't matter how. Note in this case, the repeating unit is this entire thing, because we've not got one molecule reacting. We've got 2 different molecules coming together, to form one repeating unit. So this entire thing here is the repeating unit. So don't try just drawing half of it, because that obviously isn't correct. The repeating unit is the entire thing from carbonyl group right through to O, and obviously the trailing bonds there as well. So as I said, this is terylene. Then this is an example you are expected to know, plus water, of course, there again. You're expected to know this, and then it's a polyester and the reactants here, the benzene 1,4-dicarboxylic acid and the ethane 1,2-diol. That is very important. Right. Next one, done with polyesters now. We're going to move on to look at some polyamides. And polyamides, the first place you'd have seen polyamides, or polyamides are also how proteins form. So amino acids coming together to form polyamides. So dipeptides and all the rest, they are polyamides. Not going to look at those now. I'm going to look at two specified examples, and those are Kevlar and Nylon. So the first one then, the production of nylon 6,6. So nylon 6,6. Interestingly, nylon coming from supposedly where it was made, New York and London. I don't know if that's true or not, but there you go. Nylon 6,6 is made from two similar molecules. We have hexane diavic acid, so something like that. It's easier to abbreviate this central portion. You by all means can draw it out, but obviously you've got it's going to take you extra time. And then on this side we've got 1,6-diamino-hexane. A couple of points I'd like to write. Well, one real main point here. Obviously, I've abbreviated the central portions. Be aware that this is CH24, whereas this is CH26. If you put CH24 there, that's going to be 1,4-diaminobutane. It's got to have those 6 there. The reason you only need the 4 here is because obviously we're capping it each side with our carboxyl group, each one which provides as a carbon. So do not make that error there. That would be an absolute schoolboy if you were to do that. So make sure they're drawn out fully. Names of these, just so you can see those: hexane dioic acid and 1,6-diamino hexane. These are going to join as is this. Let's go slightly different colour. There we go. Similar to before, but with a reasonably large difference actually. Let's go through here. CH2, 4, CO. Notice there is no oxygen there. We're going straight. We'll do it at the bottom. I think it looks slightly neater like that. There is no need to have any oxygen here left over. The OH and the H come together in their entirety. So there is no need. It's just C to N. Going across here, NH, and then there's a trailing bond there. So each side, we're with a carbonyl group on one side, and this partial amino group here. And of course, what we have in the middle here, we have amide linkage. And this is where we get this term polyamide from. So the amine group being that carbonyl with the amino group added onto it, and that's exactly what we hear, amide linkage. So it's not an ester, a polyester rather, it's a polyamide. Specifically this one being nylon 6,6. You are expected to be able to draw the repeating unit, which is this entire thing here, and you are also expected to know the products of that as well. So a bit of a tricky one to do. Once you remember the names though, all you've got to do is remember the names of the molecules that make it. You haven't got to remember how it forms, because that's pretty straightforward. You can just do that on the fly. Next one. Oh, some stragglers on the side here. Just get rid of that. Next bit then is going to be another polyamide. This one's going to be Kevlar. So Kevlar is a polymer. It's a polyamide polymer. Used in, obviously, vests and all the rest, protective clothing. Also used in various sort of where high strength is required. I'm trying to think where else you use Kevlar now. Possibly in sports equipment as well, maybe. But certainly in bulletproof jackets, stab-proof vests and all. Bulletproof jackets, is that right? Bulletproof vests, whatever they're called. So Kevlar, again, you're expected to know the names of the initial molecules. So the first one, a dicarboxylic acid. over here. So there we have that nice aromatic structure, which we actually used earlier on. And then the next part is, again, because we're producing an polyamide, we have to have an amine based molecule, and again it has this aromatic portion to it, with the obviously the nitrogen there, the hydrogen, and the hydrogen. Now, in terms of names for these, our names are going to be benzene, 1,4-dicarboxylic acid. So exactly the same as what was used in the formation of terylene, same initial product there. Oh, sorry, same initial molecule. And this one here, benzene 1,4-diamine, named as such because we have this 1, 2, 3. There's a corner there; it's terribly drawn, but a corner 1, 2, 3, 4, and again 1, 2, 3, 4. So the amino group is on the first carbon and the fourth, and this one, the carboxyl, was on the first and the fourth. Coming together to form our repeating unit, as with all the rest, same, because it's a polyamide, we haven't got to worry about oxygens. So carbon, carbonyl group, benzene ring, carbonyl group straight through to the nitrogen. Could go up or down. I tend to draw it down. I think it looks nicer. Ring, nitrogen, hydrogen, boom, trailing bond. There you go. And this guy here, this is Kevlar, and as I say, used in stab vests and all the rest. Very useful. Good. Now, once again, you need to know the example of Kevlar. You need to know the example of I've forgotten what it was now already. You need to know the example of nylon, the other polyamide. You need to know the example of terylene or PET as the polyester. Those are specified in the specification, so you need to have them down, both drawing the repeating units and all this, but the key thing is to remember the names of the reactant molecules. The final bit really with polymers is the idea of the disposal of polymers, and it's a section which I don't thoroughly enjoy. It's that idea of sort of, it's the itty bitty kind of the bits of chemistry that come up every now and again through units 1, 2, 4, and 5. First bit is disposal of polymers, is the idea of, and this the question is occasionally asked. There was one I think that was asked. It was to do with basically Kevlar versus a polyalkene. So it could be versus polyethene. And it was in relation to the biodegradability of which one would biodegrade first, or something of that nature. And really, the way the question works is that it's that condensation polymers are biodegradable. So condensation polymers are biodegradable due to the due to the polar bonds, and it's these polar bonds which mean that they are susceptible to nucleophilic attack, in particular from things like water, e.g. water, and therefore they will break down. Polyalkenes, on the other hand, do not have polar bonds. Okay, no polar bonds in polyalkenes. The next portion of the disposal of polymers is I've made a table to try and make this whole thing just a little bit easier, rather than just sort of running through it, because it's one of those where you've got 3 particular methods that are specified, and that's landfill, or dispose of polymers by putting them into landfill, dispose of polymers by burning, and then recycling as another way of disposing of them. So this is the table, and really all you need to do is just learn this. So burying, landfill, run through it very quickly. Advantages: it's fairly cheap, it's fairly easy to do. Burying, not burning. So just stick it in some sort of landfill site, stick it in some ground. Problem is, over time the plastic will potentially decompose, can release methane, which is a green house gas, not particularly nice. Obviously takes up space as well, space that can be used for housing, space that you can use for farming. Not overall great. And also we could say it's an eyesore as well. Burning, pretty good. Gets rid of the plastic completely. We haven't got to worry about landfill. We can use the heat produced in the burning to generate electricity. That's pretty good. Problem is, things like PVC in particular can release things like hydrogen chloride. These have to be removed prior to the gases going into the atmosphere, because otherwise it's pretty bad for the atmosphere and all the rest of it. CO2 produced, probably not going to be able to remove that. That's a greenhouse gas. That's obviously going to have an effect on global warming and all the rest. Recycling, pretty good. Cuts down on landfill. We reuse the material. Saves on raw materials. Oil is non-renewable, so we haven't got to worry about that too much. And it produces less carbon dioxide than burning the plastic. However, it's fairly labour intensive to sort the plastics out. You've basically got loads of plastics. You've got to work out which ones. You can't just recycle them all together. They've got to be sorted and all the rest. That costs money, and that's part of this idea of costing more than landfill. Finally, the plastic can become contaminated in the process of recycling. So really, these are just points you need to know. I don't think I've seen any questions in the past actually specifying sort of needing to know any of these, but you never know. They could stick a question in, a little mini essay, sort of 4 or 5 mark one, compare the use of recycling to burning or something like that. But there you go, that's polymers anyway. The entirety of the topic: addition, condensation, and a bit about the disposable. So I hope that's been alright.